let's look at the question. Graph valid tree. We have a graph of n nodes labeled from 0 to n-1, and we are given an integer n and a list of edges, where the edges at I is the list of the nodes AI and BI, which indicates that there is an undirected edge between nodes AI and BI in this graph. And we need to return true if the edges of the given graph make up a valid tree, and otherwise it returns false. In the first example, we have 5 nodes, which is 0, 1, 2, 3, 4, and the edges are 0 and 1, 0 and 2, 0 and 3, and 1 and 4. So the n is 5. And let's try to form a tree, 0, 1, 4, and 0, 2, and 0, 3. Yes, it is a valid tree, so we should return true. In the second example, we also have 5 nodes, which is also 0, 1, 2, 3, 4, and the edges are 0 and 1, 1 and 2, 2 and 3, 1 and 3, and 1 and 4. So let's try to form a tree. We start from 0, 0, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So the 1, 2, 3 is a triangle circle. It is infinite, so it is not a valid tree. We return false. So in the first approach, let's try to combine graph theory and iterative deep first search. Intuitively, we will note that the same approach will also work in recursive deep first search and iterative breadth first search. And let's recall a graph G. What makes graph tree? It should meet the 2 conditions. The first condition, we should make sure that G is fully connected. In other words, for every pair of nodes in G, there must be a path between them. And the second condition is G should contain no cycle. In other words, there must be exactly one path between each pair of nodes in G. So here, we use the depth first search, which is a classic graphic traversal algorithm that can be used to check for both of these 2 conditions. So for the first condition, we should check whether G is fully connected. If and only if it is fully connected, we can start a depth first search from a single source and discover all nodes in G during it. And for the second situation, we should check whether G contains no cycles. If and only if there's no cycle, we can execute the depth first search, which will never goes back to an already discovered node. And we need to be very careful though, not to count the trivial cycles, like the form of node A pointing to node B, but node B connect back to node A. So that occurs sometimes with most implementation of the undirected edges. So first, we import list from a module called typing, and then we define our main function, define valid tree, which have a variable n represent the integer, how many nodes we have, and another variable is the edges, which indicates the connection information. The edges is a 2D list array, and inside the list it also have the sublist, and inside the sublist it is an integer, 2 integers, indicates that 2 nodes connection information. So it forms a sublist and it contains a lot of sublists. This is our 2D list, and then we return a Boolean value which indicates whether this is a valid tree or not. So before we write our algorithm, first we should check the edge case. If the length of edges is not equal to n-1, that have 2 situations. The first is length of the edges less than n-1. That means we have less edges than the nodes. That means it haven't been fully connected. Some of the nodes isn't fully connected. In that case, we return true. That is not fully connected, means it is not a valid tree. Another situation is length of the edges is greater than n-1. In that case, we have more edges than the nodes, so they have more nodes connected more than once. That means it will form a cycle. So if it forms a cycle, it is also a not valid tree. We also return false. If we want to use depth-first search, it requires us being able to look up the adjacent of a given node, which is intermediate neighbors. Like many graph interview problems though, the input we are given doesn't allow us to quickly get the neighbors of a node. So therefore, our first step is to convert the input into an adjacency list. Let's recall, an adjacency list is where we have a list of sublists, where each sublist is the list of intermediate neighbors for the ith node. So first we have an input list edges. It has 4 sublists, which represents each edge, and we use 2 pointer AB to go through the whole list. And the input element is 0, 1, 0, 2, 0, 3, and 1, 4. And then we create an empty list represent the adjacency list, and inside the adjacency list we create 5 empty sublists represent 5 nodes because n is 5, so the length of the adjacency list is also 5. The process is first we add the edge at B to the position at A, which is at 1, to the adjacency list at node 0, and then we add the edge at A, which is 0, to the position at adjacency list at 1, which is node 1. And then we add 2 to the node 0 and add 0 to the node 2. And then we add 3 to the node 0 and add 0 to the node 3. And then we add 4 to the node 1 and add 1 to the node 4. So which is alternative, add them to the corresponding list. So now let's create a variable adjacency list, and it is an empty list. We'll create a new list for it, and then inside it is an empty list. We initialize this empty list for each node. We use a for loop for underscore in range from 0 to n-1, so that we generating the empty list. Then we can print out the adjacency list to check it out. Yeah, it have 5 empty lists represent our nodes. And then we use a for loop for A and B in edges. We just input the value to the AB. The AB will go through as 0, 1, 0, 2, 0, 3, and 1, 4. And we will go through the edge list. We just popping them to the adjacency list. Adjacency list at position A, we append the value from B. And the adjacency list at position B, we append the value at A. So finally, we get what we want. 1, 2, 3, 0, 4, 0, 0, and 1. And before we actually move on carry out the depth-first search, let's quickly reassure ourselves that an adjacency list was the best graph representation for this problem. And there are also other choices would have been whether an adjacency matrix or a linked representation. An adjacency matrix would be an acceptable, although not ideal representation for this problem though. Often, we'd only use an adjacency matrix if we know that the number of edges is substantially higher than the number of nodes. So we'd have no reason to believe that is the case here. The second approach is linked representation, which will provide some useful insight into this. A linked representation, where you make actually node object, would be an overly complicated representation and could suggest to an interviewer that you have limited understanding of the adjacency list and adjacency matrix, so they are not commonly used in the interview questions. So there are 2 checks. The first check is very straightforward. If the graph is fully connected, then every node must have been seen. This means that all nodes must be in the same set at the end, because a set removes duplicates, and only the values going into it were valid node numbers. Then we will know that the graph was fully connected if and only if the scene set contains n values at the end. So we just contain the size of the scene set with the node n. So if it is not equal, we return false. That means the depth first search isn't discovered all of the nodes. And if it is equal, we return true because the depth first search already discovered all of the nodes. So for the second check, you may be thinking, can't we just modify the algorithm to return false when a neighbor is visited? Let's say if scene set contains the neighbor, we just return false. However, this would only work on a directed graph. So on an undirected graph, like the one we're working with here, the trivial cycle will be detected. For example, if there's an undirected edges between the node A and node B, a detected cycle will be include the node A connected with node B, but node B connect back to node A. So this is because an undirected edge is actually two edges in the adjacency list. And so it will form a trivial cycle. So all undirected graphs are actually two-way directed graphs. While excluding the trivial cycle, there are several strategies of detecting whether or not an undirected graph contains a cycle, mostly rely on the idea that a depth first search should only go along each edge once and therefore only in one direction. This means that when we go along an edge, we should do something to ensure that we don't then later go back along it in the opposite direction. So here are a couple of ways to achieving this. So the first strategy is we just simply delete the opposite direction edges from the adjacency list. In other words, when we follow an edge from node A to node B, we should also look up the node B's adjacency list. We just delete the node A from it. So it will effectively removing the opposite edge from the node B to node A. Let's input the list 1, 2, 3, 0, 4, 0, 0, 1, and it represents the adjacents from the node 0 to node 4. The n is 5, it represents they have 5 nodes. So all of this is the adjacency list we get at the last algorithm. So we use a stack to keep track of the unexplored nodes. We push 0 to stack initially, and then we use a set scene to keep track of the already seen nodes so that we can avoid infinite looping. And we add 0 to initialize the scene. So we use a while loop here. While there are nodes remaining on the stack, we take one element of the stack and pop them to visit as a node, and then we check for the unseen neighbors of these nodes. So if the scene set contains neighbors, then that means we already seen the node. Then we just return false. That means it is not a valid tree. So we return false. It can avoid infinite looping. And otherwise, if we unseen the neighbor, we just push the neighbor onto the stack and record that it have been seen. So we just add the neighbor to the scene set. This time, we remove the element of the adjacency list as neighbor at nodes, which is the first element in the node 1, and then we keep move on our neighbor. This time, the neighbor pointing at 2, and we append these 2 to the stack, and also add them to the scene set because we never seen them before. And then we remove the element at the adjacency list at node 2 at 0, which is 0, and then we keep move on. This time the neighbor pointing at 3, and we just append the 3 into the stack and add a 3 to the scene because we never seen it before. And then we remove the adjacency list at 3 at 0, which is the element 0. So we already check all of the elements in the adjacency list at node 0, and then let's now check another node. This time we just pop 3 to the node. Now the node is 3, and we check the adjacency list at node 3, which is empty. And then let's move to the another node. This time we pop 2 to the node variable, and we check the adjacency list at 2, which is also empty. So we keep moving on. So this time we pop the last element 1 to the node variable. Now the node is 1, and we check the adjacency list at 1, which have only one element, which is 4. Now the neighbor is pointing at 4, and then we append this 4 to the stack, and then we add them to the seen list because we never seen this 4 before. And then we remove the element at the adjacency list at 4, which is element 1, and then we finish checking the adjacency list at node 1 so that we keep move on. We pop the element 4 from the stack into the node variable. Now the node is 4, and we check the adjacency list at 4, which is an empty list. So at this time, there's no nodes remaining on the stack, so we break up the while loop while stack, and then finally we check the length of the scene. The length of the scene set is 5, which is equal to n is 5 nodes, so we return true to indicate that it is a valid tree. So first, we set a set to keep track of the already seen nodes so that we can avoid infinite loop, which is the variable scene. It is an empty set, and we can print out to say what happened. It is empty set, and then we add one element to the scene, and let's say 0 to the scene. It now had one element 0, and then we use a stack to keep track of the unexplored nodes, which is stack is 0 element, start from 0, and then we use a while loop while stack is exist. That means there's nodes existing remain on the stack. At that time, we take off the one element to visit it, which is pop the last element from the stack into the node. And then we check the unseen neighbor of this node. We use a for loop for neighbor in adjacency list at node, which is all the children's node of that node. We use a neighbor as a pointer to find all of them. So if the neighbor is in the scene, that means we've seen that before. If we already seen this node before, then we return false because it have a cycle. If it is have cycle, it must be not a valid tree, right? So otherwise, we should record what we have been seeing, which is add them to the scene. Scene.add, we add a neighbor we just seen before. Now it's marked as record as we seen before, and then we should append the neighbor into the stack. Stack.append by neighbor. And then after we finish them, we should record a link that goes to the opposite direction, which is adjacency list at neighbor. We should remove that node because this link goes to the opposite direction, right? We should remove that to avoid trivial cycle. And after finish them, we just return the length of the scene. We compare the length of the scene with n. If they are the same, it returns true. That means we have seen the same amount of nodes with the initial n. If it is same, it is valid tree. It is true, it is valid tree.